Hello, my name is J. Michael Burgess. I'm a postdoc at MPE studying gamma ray burst, and today I want to talk to you about the physical implications for gamma ray burst jets that are implied by physical fits to their spectra. For those of you that don't know what a gamma ray burst is, or more curious about what I mean when I talk about gamma ray burst. Gamma ray bursts are explosions of hypermassive stars that result in relativistic jets and relativistic outflows that expand out from their progenitors. That's an artist conception, but this is really more how we think about jets as observers and also to some extent as theorists in the field, is that you have this hyperrelativistic jet that's expanding outwards. At some point, it's optically thick to radiation, and then it will become optically thin. It will have perhaps emission from a photosphere at this point, and then the energy can be dissipated far up above the photosphere, and you can have shocks or magnetic reconnection, some type of process which accelerates particles to high energy, and then they can emit optically thin emissions such as synchrotron, inverse Compton, etc. This is basically the point of understanding we are for the prompt emission of GRB in the current field. So I know this is a plasma physics conference and it's focused on theory, but it's important for theorists to understand the observations that we have so that you can understand how we come to the conclusions about what we think is going on and how you can better make predictions that will align with our data. So let's talk about what the observations are that we have. To the right, you see a count spectrum from Fermi GBM of a simulated gamma ray burst. So what you'll see on the x-axis here, this is the energy, but it's reconstructed energy. It's not true energy. It's not the energy of the photons. It's the energy of channels that the instrument observes. The spectrum is Poisson distributed. We have counts, so reconstructed photons in the detector. But this is not the type of spectrum that you typically predict with some type of simulation or theoretical idea. Typically, you work in what I will call photon space, and this is photon space, but in a new spectrum. And this is actually the band function, which we'll talk about more in a moment. But how do you go from this photon space to this data space? Well, instruments that detect gamma rays have a highly singular instrument response. So you can see that it's linear in the center, but it has all these nonlinear effects that come off of the center. And as I said, it's nonlinear. You can't invert this response. You can't go from your observed data to what the true spectrum looks like. You can only go one way because it's singular. And this is the process that we have to do when we do spectral fits. We need to make a prediction over here and then fold it through and use statistics to compare that prediction to the observed data. Now, since this matrix is singular, it presents us with a problem. Two models that look quite different in new space or photon space can look very similar in data space. So here are those models folded through the response, the actual observed Poisson data, and you can see that they look almost exactly the same, even though they look quite different in new space. And this leads us to a huge problem, because for a long time in GRB physics, we'll cover in a moment, we've been using empirical functions and their shapes in new space fitted to the data to make inferences about what types of physics are occurring in GRB jets. So if you're unfamiliar with the whole story of what's going on in GRBs, typically for the past 20 years, even longer now, people fit what's this empirical so-called band function, which is a smoothly broken power law that has three characteristic properties. It's low energy slope alpha, it's new peak energy, and it's high energy slope beta. However, most of the physics is typically done with just using alpha. So if we observe a catalog of GRBs with BATSI or Fermi GBM, what observers do is they histogram the values of alpha. And since high energy radiative processes are really differentiate below the peak of their spectrum. In other words, if you want to know optically thick thermal emission versus synchrotron emission, the predictions all basically change the value of alpha. There are other predictions, but this is what people have concentrated on for years. And so if you're below a certain value, we would say that, okay, this is slow-cooled synchrotron. And if you're below an even steeper value, then you say, okay, that's actually fast-cooled synchrotron, and everything up above would be thermal emission. And so for the longest times, theorists and observers have worked together to make better predictions for what theoretical model predicts which alpha and who can capture the greatest part of this alpha distribution to say it's actually this model. However, in about 2014, during my PhD, we started fitting physical synchrotron models to data, and then quickly followed by Bing Zhang's group. And we found that actually, even when you could predict, when you would observe an alpha that would violate the so-called line of death, or the alpha couldn't be explained by synchrotron, you could still fit a synchrotron-like model to the data. This presented a bit of a conundrum, and we also know that photospheric emission, models of emission that predict emission very close or below the photosphere, they can predict a wide range of alphas that can almost cover the entire alpha distribution. So we said, okay, this maybe using alpha alone is not a good way to try to infer physics with an empirical function from the data. So a few years later, some observers came up with another idea, which is the spectral width. So instead of just looking at the low energy slope, perhaps we could take into account the width of the band function. Fit the band function to some data, then you take the width and you try to infer physics from that. So there's two ways you could measure the width, both proposed by different authors. You can either take kind of a quasi full width half max, or you can compute the angle between the high energy spectral indices normalized to the peak. And so if you do that, the idea is quite simple. Black body or thermal emission is a bit narrow, or it's a very narrow spectrum, and synchrotron is a very broad spectrum. And so if you go through and take the catalogs, instead of histogramming the low energy spectral indices of the emission, you could histogram the observed width. And the idea is very similar to alpha. If you are very narrow, you're on this side of the chart, you have thermal emission. If you're on the other side of the chart, you have synchrotron emission. And lo and behold, it looks like synchrotron is kind of ruled out again. Most of the emission would be thermal, even over half compared to the alpha distribution. So I looked at this and I said, okay, well, we knew that we had problems with alpha. Would the same kind of things come up with the spectral width? So I fit a whole lot of GRBs, several hundred, to a very simple synchrotron model, steady state model. And these are two of those fits. And as you can see, they actually look quite nice. This is in count space. Well, we can take both of those width measures, either the full width half max or the angle, and we can compute exclusion zones. So if your measured width by fitting to the band function lies here, then synchrotron should be rejected, but over here it's okay. So some of these fits, and the darker the color, the better the fit to synchrotron. Some of these fits to synchrotron that we deemed okay, they lie in this region. And then there were a whole lot of fits that were rejected as synchrotron, being able to be fit by synchrotron, and they lie kind of all over the place. But if we look at the entire catalog of fits that could be accepted by synchrotron, you see that there's a lot that actually lie deep in this exclusion zone. In fact, the two fits that you see here are some of these that are very good fits to synchrotron, but they lie deep in this exclusion zone. Why is this? It's because, again, we're trying to use empirical functions in new space to do physics. And since we already know that two different models can fit the data very well, but look very different in new space, this could lead to problems. So this is exactly what's happening here, is that the band function has a naturally narrow curvature. So it predicts very narrow spectra, whereas it doesn't necessarily mean that if you were to also fit that spectrum with synchrotron, you wouldn't also get a good fit. So you would reject a synchrotron fit even when it's actually a good fit. So where do we go from here? The idea is that we don't want to do this thing where we fit an empirical function, fold it through our instrument response, use statistics to make sure that the model fits well, and then try to infer physics from these in new space from these empirical models. We want to get rid of the band function and actually put the physics at the front of the response. So we want to fold physical models directly to the data. And that's what me and my colleagues started doing a few years ago in a little bit more detail than we had been doing in the past. So the model that I'll be talking about that we're fitting currently is a synchrotron model where we inject a power law of electrons and we basically solve the Fokker-Planck equation, and we let them cool by synchrotron. And this means that we can numerically solve all the different stages of synchrotron emission from its injection all the way to its deep fast cooling regime. And it's a physical spectrum. And we can measure things like at what value the cooling Lorentz factor is, so how far the electrons have cooled during a radiative time step, the index of the electron and of the injected electrons, as well as the magnetic field strength, which is multiplied by the injection energy. So we actually measure the multiplicative factor of those. And so we actually fit these spectra to the data. So this animation is just showing all the ranges of spectral shapes for a given injection spectral index of the shapes that we can get to the data. It's not a static synchrotron model. How do we do this? Well, this is a theory talk, so I won't go into statistics, which is a deep love of mine, but we have to use the proper statistics to fit the data. If you don't, you'll get wrong answers. Just beware when you see chi-square fits to Poisson data in Fermi-Lat or Fermi-GBM or BAT, Swift, etc. So if we want to take a look at the results when we fit this more complex synchrotron model to the data, at the top here, this is in data space, and the colored spectra are the model folded through the response, and so that's the result, Fermi-GBM and Fermi-Lat. And these are 3 different time slices. And then at the next row, we see the posterior distribution of the spectrum, and as well as the cooling and injection frequency of the emission. So you see here the electron emission the electron distribution is not cooled at all, and later on it becomes much more strongly cooled. And we can also fold the posterior back into the electron equation that we solve with Ching and Cooper. And we can look at the posterior distribution of the electrons. So again, not cooled, mildly cooled, and very fast cooled. And we fit this to 168 time resolved spectra, 18 different GRBs with redshifts, so that we could go back later and compute physical things. And we saw that this was a very common pattern in the GRBs, as well as out of the 168 time resolved spectra that we fit, only 3 were incompatible with synchrotron emission. So it looks like synchrotron can actually explain a large majority of the GRBs, at least for the not special subset of GRBs that we chose for this study. How do we analyze and make sure that we understand that these are good fits to the data? Again, this is a theory conference, so I won't spend a lot of time, but we use something called posterior predictive checks, which allows us to predict future data from the data that we fit. If you have questions about this, we can talk about it over coffee, but there is no such thing as goodness of fit. Probability theory says use posterior predictive checks if you want to know if your data are well fitted. This is what they look like. So the true data is in red here yellow here for 3 different detectors. The predicted future data is what you see in these shaded regions. We make many simulations of the data from the posterior, and it looks like you can see very well that the predicted data from the model match with the observed data. We have another way of showing that is by integrating along the observed data axis and the predicted data axis to something called a QQ plot. And so the idea is if this future simulated data follows this one-to-one relation between the observed net counts and the predicted net counts, then you have a good fit. And this is what a bad fit would look like. And we also simulated this process to make sure that we understood how this fit checking technique worked. And that's how we arrived at the conclusion that 3 of the spectra that we observed were not a good fit to the data, but the rest were. Okay, so now that we are confident that synchrotron can fit the data, what kind of physics can we learn from fitting these? So we can look at the ratio of the gamma cooled to gamma injected. So in other words, or how much the electrons have cooled in a given time step. And if you're familiar with the slow and fast cooled problem in GRBs, if your gamma cool is below gamma injected, then in this region of space you should see that's where the posterior distribution where you peaked. And if you're on this side, then you would say it's slow cooled. So as you can see, it looks like most of the spectra are moderately fast cooled. So they're near this fast cooling regime, but they're also kind of in a slow cooling regime, which presents a lot of problems for GRB emission theory, right? Since we need a lot of emission, the electrons need to, the synchrotron emission must suck all the energy they possibly can out of the electrons, so they really should be fast cooled. And from radial and variability constraints, we should really see that the electrons have had enough time to completely cool off after they've been accelerated by whatever process, magnetic reconnection or some form of Fermi shock acceleration. So this is a bit of a conundrum. However, why have we not seen this before? We knew in the past that maybe synchrotron was ruled out because of these band function indices. Well, we went back and fit every single one of these observed spectra with synchrotron and band, and then we can histogram the posterior distributions from the band fits. So if you remember, if you're on one side of the line, then you would say, okay, synchrotron is accepted, and if you're on the other side of the line, synchrotron is rejected. But this histogram is only of the good synchrotron fits. In other words, if you're here, you should be ruled out by synchrotron. Okay, well, we can allow for maybe uncertainties in the measurements, whatever, but these alpha values historically would say, okay, no, you cannot be fit by synchrotron. But definitely here, where alpha is approaching positive values, where you would expect to see, expect that the emission would look more thermal, you can see that there are even some alpha values out in this regime. And so in other words, if you were to fit that with a band function, you would rule it out as being fit by synchrotron, but we know that we can fit synchrotron to these emissions. And that is kind of interesting. So why is that? Well, again, there's two things. First, synchrotron emission asymptotically does have these two fast and slow cooled low energy spectral indices, asymptotically. But there's a whole range of curvature in synchrotron emission depending on the inputs for the electron distribution, injection, where you are in the cooling regime, et cetera. So using a more physically correct synchrotron emission could solve this problem. But it's also back to this energy dispersion problem we discussed earlier, that two very different spectra in nu can look very similar. So I selected two of the very hard or very positive alpha fits that were good fits to synchrotron, but would have been predicted to be thermal emission because of their band function fit. So here's an example of one. The red is the band function fit with an alpha of around 0.5, and here's the synchrotron fit to the data. Both of these are good fits to the data, but they predict very different spectra in real photon space. And similar, this is one with a very, very hard alpha. So it just means that, once again, we cannot use empirical fits to data to make physical inferences about GRBs. So we need to throw away concepts like the line of death, etc., and we need to just fit physical models to the data in order to understand what's going on. And that's just because of this whole concept of energy dispersion. And for those of you that aren't gamma ray astronomers and used to this kind of thing, I'll just give a little example here. Imagine that you have a telescope and you want to observe the shape of some object. That the shape of that object, the true physical shape, is just a circle. But because of atmospheric effects and some detector effects, you observe actually a dispersed image. It's kind of fuzzy, right? So this is image dispersion instead of energy dispersion. Well, say you have some empirical model that looks like this, right? It's got spikes on it or whatever. It's just some very simple mathematical function that you can fit to the space. And because of energy dispersion, you'd be able to fit that. Well, then if you took the fitted result from that and plotted in the equivalent image nu space, you would say, okay, well, now how do I infer some shape physics from this? Well, I can't fit my physical circle model to it anymore because the spikes are there and my circle model can't predict the spikes. And that's very similar to what we've been doing with the band function and then trying to go back to physics. Okay, so if we can fit physical models to GRBs, what are the implications for the jet structure and the plasma in the outflow? So my colleagues and I, we derived two limits for the bulk Lorentz factor of the expanding jet. So if we assume from gamma-gamma opacity, we can derive a lower limit of the bulk Lorentz factor, how fast the jet is expanding, from the highest energy photons that we observe in the outflow from the FITs. So that gives us a lower limit. And the fact that we are observing optically thin emission and we don't observe a photospheric component at all, we can derive an upper limit for the bulk Lorentz factor. And we even conservatively allowed there to be a 50% energy flux subdominant photospheric emission that we would actually have been able to observe if we'd looked for it. But in other words, this upper limit is a bit conservative, so we do allow for some photospheric emission to be there. So we can derive from these fits the posterior for both this upper limit and lower limit. So if I plot the lower limit from all the fits onto this plot, this is where they lie. And we just took the peak flux upper limit since for visual simplicity. Now we plot the upper limit. You notice that for every single GRB, the upper limit is below the lower limit. This means that if the emission is synchrotron, if it's synchrotron, then the standard fireball thermally accelerated jet of GRBs doesn't work. If you fit with a photospheric model and find that it's a good fit, it's possible that it could work. But if the emission is synchrotron, for the sample that we've observed with redshift, you cannot apply thermal acceleration of the jet. You need to go to something like magnetic acceleration. So we went back, recalculated the parameters using a bunch of different things, which we can talk about in deeper discussions later in the week. But by making some more assumptions using our synchrotron fits and the physical parameters we derive from them, we can derive the distributions for the bulk Lorentz factor given different levels of magnetization. So psi b here is the level of magnetization. The color is the cooling regime of the electrons derived from the fits. And we can do the same for the radius. And we found that in order to keep the radii from being far, far too high, so 10 to the 17 we would consider to be too high, you have to have pretty moderate magnetization. And also you need to have an additional Lorentz factor on top of the bulk outflow. So something like these mini jets that have been proposed by other authors in order to keep the variability timescales under control. So the implications, again, from our synchrotron fits are that if you have synchrotron, the emission must occur at pretty high radii. You need some magnetization in the jets, and you possibly need to have some more complicated physics going on about the outflow rather than just the bulk outflow of the jet. So these are the results if synchrotron is a good fit to the data, and if you accept that. What about polarization? I'll just briefly go over the fact that for some of these GRBs that we've also fit with synchrotron, we've also observed them with the gamma ray polarimeter POLAR that was on the Chinese space station. It's not working anymore, but we're building the second one right now. I'm the project scientist. It will be 4 times as big, and we will get many, many GRBs with very nice polarization measurements. But we were lucky enough to have one observation, several, but one really good observation between POLAR and GBM, where we were able to locate the GRB using GBM very, very well, which allowed us to really lower the systematics for the polarization measurement. And we derived very complicated polarization and spectral likelihood, so we could do simultaneous polarization and spectral fit. So the two different parts of the data talk to each other. And we folded synchrotron emission into both the polarization and the spectral response. These are the results. Again, that's not very interesting to theory community, perhaps, but it was very nice because we saw that both the instruments are well calibrated to each other, and also synchrotron was a really good fit to even the POLAR data, as well as the GBM data simultaneously. But maybe the most interesting results, and these will get better with a bigger instrument, is that in these different time slices, where time is going 1, 2, 3, 4, 5, 6, 7, 8, 9, here the data wasn't all that great. We observed at the beginning no polarization, so polarization is on the radial axis here, and the polarization angle is the circular axis. And then all of a sudden we start seeing polarization, but as time goes on, the polarization signal grows, and we start seeing a rotation of the polarization axis with time. And then the data get a bit too weak for us to observe anything, but we have hints that the polarization axis is still rotating. So we see moderate polarization, the spectrum is fit by synchrotron, and we see a rotating polarization axis. Now, since we know that the polarization angle is rotating, that means that if we had better data, we would be able to go to finer time bends. And since the polarization angle is rotating, it means that we likely have much higher polarization than what we could observe. It's just that the polarization signal is canceling itself out with the rotation. So we need a bigger detector, which is what Polar2 will provide. But these are pretty interesting results. And again, kind of more, maybe not smoking guns, but nearly smoking guns, that synchrotron emission might be what we're observing in gamma ray burst. So just to wrap up, we need to stop using empirical functions on data. So if you have very good physical models that you want to fit to GBM data, let us know. We know how to fold them through the response and do this type of analysis. We're doing it now with some other photospheric models. We're working with Emmanuel and Cironi and Belobordov to fit their synchrotron models to the data now. We're working with SF-Pair to fit his photospheric models, but stop kind of using these old line of death, band function, or spectral width arguments because they don't work. And the main takeaway from fitting synchrotron to the data is that if it's synchrotron, the emission is at high radii. Somehow the electrons have to be re-energized in the flow. We don't know how that happens. And the jet is definitely magnetized if it's synchrotron. So thank you very much, and ask me questions in the slides. Thanks.